Hello everyone, my name is Pedram and I'm a professor in data analytics. Welcome to another episode of Deep Learning. Alright, Module 5, Deep Computer Vision, and this is the part 3 and last part of the Python lecture. So the prereq for this Python lecture is, I assume that you have already watched part 1, part 2, part 3 of the theory lectures. You're familiar with the CNN architecture and you know the concept of transfer learning, and now let's do these things in Python. Okay, so let's go to the GitHub account. This is a GitHub repository for the course. Go to lectures and codes and module 5 Python, and we are going to work on this one, transfer learning. We have already covered in part 1 and part 2 of the Python part, we covered these two files. So now let's talk about the transfer learning. So a quick note that previously we used to work with the dataset that we're already built in Keras API. So we didn't deal with importing real world images, right? In this one, we are going to do that. We're going to see how we can handle the real world images, right? Let's say, for example, images from your phone or images available in Kaggle competition, things like that. Okay, the JPEG image and with different extensions, right? Okay, so let's go ahead and open it. And we are going to work with Google Colab. So specifically for this one, because we're going to do fine-tuning using transfer learning and we're going to do some kind of data augmentation, I highly encourage you to use Google Colab unless you have a good GPU, right? Because I think and this is almost March 2023, and as of now, let me see actually. The GPU that Google Colab offers for the free tier, it's actually a very decent one. It's usually the Tesla T4. Let me actually quickly check that one. And that's a decent, that's a very decent GPU for this task that we're going to do. It used to be in the Pro tier, the one that you have to pay for subscription, but now I think it is also available in the free version. So this in this my Google account, this is a free version, so let's check it out. So you have to type in NVIDIA and then SMI. Let's see what GPU we have. So this is Tesla T4. As I said, unless you have a better GPU, I highly encourage you to just use Google Colab, the free tier. Awesome. Okay, so let's talk about the data set, right? This is an important part. And we want to work with real world images, let's say the JPEG images, right? And just a quick note that the source of this notebook, I think plus 70% of this notebook is coming from here, Francois Cholet, his awesome deep learning with Python notebooks. So this is his GitHub account. You can get access to all these notebooks from the book here, and I am using from chapter 9. I'm using it's a combination of all these 3 notebooks. All right, so and the data set is going to be dogs versus cat data from Kaggle. So let me go ahead and show you. So this is type of images that we're going to see, right? So these are it's a large data set, 853 megabytes, relatively large. And these are real world images, right? So let's say how we can deal with this. So what is inside this data set? We have a test1 zip file and train zip file. What we're gonna do, we're gonna go ahead and download this and then unzip it, and we're gonna divide this train set into 3 subsets: train, validation, and test. And obviously we're not gonna touch this one. Okay, so there are 2 ways you can do things like this. You can go ahead and download it directly from Kaggle, or you can download it by using Kaggle API inside the Google Colab, and this is a preferred method. If you scroll down, for example, if you have a Kaggle, if you have a Kaggle account, you can download the API keys, and then after that you can simply run this line of code in your computer or Google Colab. Then automatically it's going to go ahead and download these files for you. So this is the preferred method, and I'm going to do it that way. So let's go back. So as I said, you need to have a good Kaggle account. So let's go ahead and see that. So for example, I go to Kaggle. I already have an account. Then you have to go to your account settings. So go to account. Then if you scroll down, you should find the API section. in the API section, you can go ahead and create new API token. So this is a JSON file. It's basically a very simple dictionary. I'm going to go ahead and show you the name and the let me open it up. So in VS Code and the key. So don't worry about it. I know this is supposed to be private information, but after I record this video, I'm gonna go ahead and decease this. Basically, I'm gonna go ahead and expire this API token. Okay. So you have to use your own API because again, this one that you're going to see is not going to work by the time that you're watching the recording. Okay, so I downloaded that one. It's in my download folder. So let me actually pull it up. So it should be somewhere here. So this is a Kaggle.json. And as I showed you earlier, something like this. It's a very simple dictionary. So we have the username and key, and now we are ready to run that line of code in Google Colab and download the data, right? Again, alternatively, you could have downloaded manually and then uploaded in Google Colab, but obviously this is a lot more efficient. Okay, so I'm gonna go ahead and do that from Google Colab, import files and files.upload. So I could have done it something as simple as this, upload, okay? All right, so when I click on this, it's waiting for that JSON file, so I'm gonna show the location. So it was in my download folder. This is a JSON file. This is the username and key that you were seeing, okay? All right, so let me go back to Kaggle and show you something. It says that when you create your new API token, it says that ensure Kaggle.json is in the location of the root, then .kaggle /kaggle.json to use the API, right? So we have to go ahead and create this either in your local computer or Google Colab. So we are doing things in Colab, so let me show you how to do it in Colab, right? So we're going to do that. We're going to say, we're going to make that directory, I'm going to say make directory, then in the root.kaggle, and we are going to copy this thing that you already uploaded, right? If I refresh this, Kaggle JSON is here. We're going to copy this Kaggle JSON to this folder that we just created, right? So this is a folder that we just created. And also we want to make sure that this file is only readable by the current user. If you want to do that, you have to run it in a chmod 600. Okay, so I'm going to do chmod 600 and then read it, okay? So now this the directory has been made in the root section. I'm not going to go ahead and navigate to the root because there are lots of folders and I just don't want to mess things around visually because we want to keep track of these folders. But you can go ahead and check it out that this folder is created and then this JSON file has been copied over. And yeah, here you can simply do something like this. Then now we're ready to just import the data, right? And let's go ahead and run this line that we saw here, right? Remember, where is this? It was in the Kaggle data here. Okay, here we're going to run this line of code, and because we're doing it in Google Colab, I have to add this exclamation point first, right? Mark. Let's go ahead and do that. It's going to take some time depending on your internet speed connection. And now let's see, what do we have, right? So I go ahead and downloaded it. Right now it's dog versus cat zip, so we have to go ahead and unzip it quietly. So I'm going to do unzip QQ quietly and then dog versus cat zip. This is a file, and again, it may take some time. It all depends on your internet speed connection and things like that. So I'm going to go ahead and refresh this folder. Now this is what we have, right? So if I go back to cat versus dog Kaggle website, you see there are 3 files. The 3 files are sample submission. If you have done any Kaggle competition, you know what is this. Basically it's the sample CSV file that you're supposed to submit for participating in the competition, right? Basically these are the predictions of your model on the test set. This is test 1 and train. So as I said earlier, we're going to deal with the train thing, right? So I'm going to take this one, unzip it. Now the train folder has been unzipped, okay? So this is, as I said, it's a relatively large data set, right? So now we have the train thing, right? So it has 25,000 images of dogs and cats, and 12,500 for each class. So it's a balanced data set, right? And we are going to go ahead and create 3 folders: train, validation, and test. And for this specific example, I want to work with a very small subset of this data set, not 25,000 images. I'm going to work with 2,000 image for the train, 1,000 image for validation, and 2,000 image for test. And the idea is that let's work with a relatively small data set and see how data augmentation can help. And on top of that, how transfer learning can help, right? Because what is the idea of transfer learning? We said that what if your data set is small? We have only, I don't know, a couple thousand images. This is exactly what we're dealing with here. And then we want to leverage a model, the body of a model from some of the more famous model that has been trained already on ImageNet dataset like VGG16, and this is what we're going to do. And then apply it to our own model, right? With different types of transfer learning. So that's the agenda. So yeah, let's do that. So the first thing we need to do is to make that directory, right? Because as I said, this is what's expected. At the end of the day, I want to have, I'm going to make a function called a df subset. And when I run this function, it's going to do these things. It's going to make a train folder for me. And that train folder goes from index of 0 to 1,000 for each class. So I'm going to have 2,000 cats, 2,000 dogs in that folder. Then validation set, it goes from the index of 1,000 to 1,500. Again, 500 cats, 500 dogs. So it's going to be 1,000 observations. And finally, the test set, goes from the index 1,500 to 2,500. Again, 1,000 cat, 1,000 dogs. So in total, 2,000 JPEG files, right? And so this part is pretty much it. Once you learn it, when you learn it once, you can apply it to any kind of Kaggle dataset out there. So don't fret over it right now, because it might, especially if this is the first time that you're dealing with something like this, importing data, making directories, making subfolders here. If this is something new, don't worry about it. You can copy and paste it from here, or you can simply use ChatGPT. I'm going to show you how to do that. Now with large language models, we can simply ask these kind of questions, and then ChatGPT is going to help us how to do that, right? And again, as I said, at some point, these kind of commands are going to become repetitive if you work with, I don't know, different types of data sets out there on Kaggle competition, on your local computer, and things like that. But the point is that we are making these directories. So I'm going to import OS, Shutil, and pathlibs. So this is the folder that we're going to use as original directory. We're going to make a new folder called cat versus dog small. This is a small subset of the data. And this is our function. We're going to say that we have two categories. In these two categories, cats and dogs. Make a new directory. The new directory is in your cat versus dog small. Then subset name, for example, it can be train. Then category, it can be cat, right? Then now the next thing is to copy images from the train folder to the unzipped train to this new folder. And this is what we're going to do. We're going to say that these are the file names. The file names is in order of, let's say cat and a number and an index number. And it is ordered in this data set, right? So if your data set has different formats, so you have to make sure that you come up with the right command here for the file name. But for us, we know that we have cat number 1, cat number 2, cat number 3, and etc. So this is where we are going to use index. Goes from start index to end index. And then finally, we're ready to write a for loop and then copy these files from this train folder to this new subfolder, which is a small subset of the data on cats versus dog. Okay. And for that, we're going to use the Shutil, the copy file from the Shutil package. Okay, so let's go ahead and run this, and I'll show you the output. Okay, now if I go ahead and refresh this thing, now there's a new folder. It's called cat versus dog, right? So let's see what is inside that one. As you can see, there is train, validation, test. Our train has 2,000 observation. Our validation has 1,000 observation, and our test set has 2,000 observation. So let's open up the smaller one because it's easier to load here. Now we have, as you can see, we have cat and dog. We can go ahead and click on the cat, and then this is indices, right? So cat 1. So this is, let's open a couple of them. So this is real world image. And as you can see, the sizes are different, right? So this is another thing. We have to go ahead and pre-process this data, make sure that they have all the same size. So that was a couple of cats. Let's look at a couple of dogs from the validation set. I don't know, maybe this one, yeah, and this one. Yeah, these are a couple of dogs, right? So this is an important step, and because again, this is how TF data in TensorFlow is expecting you to have for the directories, right? We should have directories with these exact names, train, test, validation, and a folder with the name of classes. So then automatically knows that the TensorFlow knows that these are the labels. For example, cat is a label, dog is a label, and of course these are inside it are the observations. Okay, now let's see what else. So as I said, we have to pre-process this data, make sure that they have the same shape and things like this. Okay, so what are the steps? We have to read this picture files. Then we need to decode the JPEG content to RGB, grid of pixels, right? Because again, we are trying to prepare this input to our TensorFlow, let's say CNN model, right? And then we need to convert these into floating point tensors. Then we can resize them. So here we're going to do 180 by 180. And you have to look at the size of the image, right? If the smallest size is, for example, 180, you can go with a smaller one, or you can get something in between. But obviously, thinking of the largest size is not reasonable, right? Then we can pack them into batches, right? So because remember, this is a point that we are going to take advantage of the GPU. We want to do parallel processing, and we're going to train the data in batches, right? So when one batch is ready, and then the second batch is going to be use another. Well, this is the parallelizing part of the running things on GPU, right? So there is this. So it seems that it seems that it's a lot of work, but the good news is that in TensorFlow there is this function called image dataset from directory. So basically, you have to have made this directory first. This is what we're going to work with, and then from that directory, we are going to make this dataset. And these datasets are these are objects as a type of tf.data.dataset, right? So this is what we're going to do. So now I'm going to go ahead and say from TensorFlow.keras.utils import image dataset from directory. And I'm going to create three pre-processed datasets, right? Train underscore dataset, validation underscore dataset, and test underscore dataset. And it's quite simple. Once the folders are ready and in this shape, and the rest is just piece of cake. So we're going to use this function image dataset from directory, and we say that where do you want to read it from? I'm going to read from whatever I call it. This is my new base directory. Remember, the new base directory was cat versus dog small, right? So it's okay, read it from there. You can specify it here, but again, this is just more efficient way of coding, right? Because you can change the name of the original directory and the target directory, and then just run the rest of the code, right? So I'm going to say, you see, from this folder, cat versus dog, go ahead and look at the train. And now inside, whatever image is inside that train, go ahead and reshape them. So this is the image size, 180 by 180. And the batch size, 32. Okay, I'm going to do the same thing for validation and test set. Let's run this. Okay, so this may take a little time, but as you can see here, it was fast enough because we have a very small data set, right? 2,000 observations for 2 classes, and it is we did it in a way that it's balanced: 1,000 cats, 1,000 dogs, 1,000 for the validation set, 500 each, and 2,000 for test set, 1,000 each. Okay, now we can go ahead and see what is inside these objects. Remember, these are tf.data.dataset objects, right? And there are some operations that we can do with the dataset object in TensorFlow. We can map a function to these data frames. We can batch them differently. We can, for example, well, actually, let me show you some of these functions. Okay, so we can go ahead and display the shape of this data and labels that we just created in the previous cell. I'm going to say, go ahead, and we know that there's going to be the output of this inside this train dataset or validation or test dataset. There are 2 things. The first one is data itself. These are the features. The second one are the labels. And again, if you're wondering where the labels are coming from, we didn't pass it directly. We pass it indirectly like this. We said that inside this validation set, there are 2 folders. It means that there are 2 labels. Okay, so it's going to go ahead and assign label is equal to cat, or whatever order you're going to use some integer 0 or 1, then this data frame knows that this cat1, this image, is a cat because it is in the folder named cat. Okay, so that's where the labels is coming from. We can go ahead and look at the shape of the feature space and the shape of the label, right? So let's go ahead and do that. Okay, so we decided to work, so this is a rank 4 tensor, right? We decided to work with 32 images. This is the size of badge. And then each badge is 180 by 180 by 3. We have 3 channels RGB. Okay, so these are the features, and this is our input feature, and this is our labels, right? We have 32 because there are 32 images in each badge, and each of them has a label. And remember, we said that in TensorFlow we want to do things like this, not only it should be a NumPy array of the kind of this, or tensor of this shape. His rank 1 tensor. Okay, we can go ahead and look at the labels batch, right? So for example, for the first batch, 32 observations, these are the labels, 1, 0, 1, 0. So maybe 1 is for dog and 0 is for cat, and etc. Right? Okay, now we can also look at the test set and see what is inside that test set. We know that it's a tensor, rank 4. These are important stuff, right? Because guys, remember, and one part of CNN is how to come up with a good architecture, that we talked a lot about it in this theory lecture, part 3, right? What is the architecture? What are the best practices? Another thing is that how to prepare the data and how to pass it to the model. So in order to understand that part, we have to know what is the shape of the input, right? So now I can see, okay, the shape of the input is a rank 4 tensor. All right, that was the pre-processing part. Let's build the CNN, and we're going to work with a very simple CNN and use it as a benchmark. Okay, now let's go ahead and build our benchmark, the CNN benchmark. So let me go ahead and minimize this one. We don't need it anymore. All right, so from TensorFlow, let's go ahead and import chars and layers. And you should be quite familiar with this function that we're putting together if you have watched the previous Python lectures. So very simple model. The input layer is basically, so the shape is important, remember? So that's why this was important. No, this is the shape of the test set, but the train set is also the same. And this shape is expecting you to give the one sample, the shape of one sample. So one sample is an image, 180, 180 by 3 channels. Okay, so this, we can call it our input layer. And then we're going to rescale it because, again, remember, these are different images. We want to make sure that, well, actually, this is the rescaling part. We already reshaped them, all of them to 180 by 180. So now we are going to say, instead of using numbers between 0 and 255, let's rescale them to numbers between 0 and 1. So this is a rescaling layer. And then we have a bunch of conv and conv followed up by max pooling layers, like conv pooling, and etc. And at the end of the day, we are going to flatten things and then pass it to an output layer. And in the output layer, we're going to use a sigmoid activation function simply because we have only 2 class. This is a 2-class classification. So we need only 1 node, and that's it. So just if you watched the theory lecture, we talked about how to design an architecture. We said that usually as we go deeper in the network, so the size is going to get decreased because we are simply using filters and for example, same valid padding. So if I use the valid padding and basically filter size 3 or 5, so of course, at the next convolutional layer, the spatial dimension is going to decrease. This gives us some computation relief that we can use more filters, right? So maybe first convolutional layer 32 filter, second 64, 128, 256, and then another 256, flattening things, and then that's it. We're going to go ahead and build our model, chars.model, inputs, outputs, and then we can call it our base CNN. For the optimizer, you can try Atom or RMS prop. So both of them are going to do a decent job. Your loss function is binary cross entropy simply because you have 2 classes. We're going to keep track of the accuracy metric as well. You can put whatever classification metric you want, which is available, should be available in Keras as well. All right, so this is our model. Let's go ahead and build that model. So I'm going to say this is model coming from this function, CNN builder. Let's look at the summary of the model. And this should look very familiar to you because we have covered all these things in the previous lectures. But look at the input shape again. for example, if I'm passing the train set, this is going to be, for each batch, it's going to be 32, right? And if you know how to calculate these numbers, and for example, let's look at a couple of them. So we know that at this layer, conv layer number 1, it's coming from an image with 3 channels. So that's why we have 3, and you have to multiply it by the filter. So what is our filter? Filter is 3 by 3, so we have 9 weights. So 9 weights for each channel, so 3 by 3 by 3, and then it's going to and we're going to use 32 of these filters, so I have to multiply by 32, and I add 32 bias terms. So this is where the number 896 is coming from. And you can do the same thing for the rest of the layers, and I encourage you to practice that one. And yeah, for example, and then when we are flattening things at the very last layer, we have, so the output of this conv layer number 5 is 32 if you're passing a batch size 32, 7, 7, 256. We can flatten them by doing something like this: 7 multiply 7 by 256, right? So this is where the 12,544 is coming from. So this number. There you go. Okay, so these are basically, and how many parameters do we have? I need to add a bias term here, so that's why we are going to add number 1, because we only have 1 node in that very last layer, which is a dense layer. Okay, and also we know that in terms of spatial dimensions, why did we go from 180 to 178? Because the filter size was 3, the padding was 0, so well, we can say 1 for valid padding. So we're going to say 180 plus 0 minus 3 divided by stride, which was 1, plus 1. So this is what I'm doing, right? This is what I'm doing. Again, make sure to watch the theory lecture if this doesn't ring a bell. All right, so 178. So this is where this number is coming from. All right, good. So let's go ahead and fit the model. We are going to create our callback, and we're going to call this model the CNN benchmark. And we want to save the best only. We will monitor the validation loss. So this is our callback. Let's go ahead and run this line. And now we are ready to train the model. So this is going to take some time. So I run it previously. I want to rerun it one more time, but I have to pause the video, right? So, but what we're going to do is that, so we have 30 batches. Sorry, batch size is 32. We have 30 epochs. We are going to use a validation data set. So maybe here's a difference between what we're doing here and compared to what we did in the previous 2 Python parts. Look at that. For train sets, I'm not passing X train, Y train. For validation set, I'm not passing X test, Y test. I'm passing only one thing, one object. And that one object is train underscore dataset. Remember, this is a tf dot, let's go back. This is a tf.data.dataset, and we know that inside that thing, there are 2 things: the data itself, the features, and the labels. So that's why we needed to only pass this thing to model fit. And the model is now being fit, right? So the first one takes 16 seconds, and the rest of them are faster. So the model starts with 50% performance in the validation set. This is the accuracy. Well, of course, it's not good, but that's the first iteration. And now, as we are going through more epochs, the model is doing a better job. So I'm going to go ahead and pause the recording and then show the results. Okay, it seems that the model has been trained. No, the very last epoch 30, we get to accuracy in the validation set 75. So it's a lot better than 50%, but there's a long way to go. We know that we can do a lot better on this cat versus dog classification. Okay, so let's see. We are going to evaluate the model. So we have seen these things before, so I'm going to speed up a little bit. I'm going to make a new data frame, and we know that there's if I do history.history, so from that dictionary I can make a data frame. What is inside that data frame? There is my loss in the train set, loss in the validation set, accuracy in the train set, accuracy in the validation set for 30 epochs, right? We can go ahead and visualize it. So this is how it's going to look like. And for accuracy, as you can see, at some point the model is overfitting. It's not improving that much. And let's look at the loss. Same story here. No, the model is getting a little better, but maybe right after epoch 10 is overfitting, and it's not able to make a better prediction. We can look at the performance of the model on the, let me go ahead and refresh this, show you something. So here is our model that we saved, CNN benchmark.keras. We can load that model, call it test model, and then evaluate this test model on test dataset, right? Remember, usually we pass two things here when we do evaluate, x test, y test, but this is a tf.data.dataset object, so we don't need to do it that way. So let's go ahead and run this, and let's see what is the performance in the test set. So it seems that here in the test set, it is 70%. So depending on, each time that you're running it, because we have different initiation weights, different random seeds and etc., you should be around plus 1 or 2%, plus minus 1 or 2%. So previous time it was 69%. Now that we're doing it together, it's 70%. On your computer, you might get a different number. But overall, you're getting a test set accuracy of around 70%, okay? Let's see how we can improve this, right? So in the previous Python part, we talked about data augmentation. So we're going to use exact same thing here. So I'm borrowing the exact same code. So it should look familiar if you have watched the previous one. But the idea of data augmentation is what? It says it's something like this. If you have a small data set, like here what we have, only 2000 train set, right? Can we do data augmentation for two reasons? First of all, to simply generate more synthetic data. And secondly, to avoid overfitting, right? So can we do something like that? And the answer is yes. And hopefully we get a better performance in the test set. So that's the goal. Let me go ahead and create my layer, call it data augmentation. It's a sequential thing, right? So we can go ahead and, for example, do random flipping. Here I'm doing horizontal. We can do random rotation, 10%, plus minus. We can do random zoom, 20%. And so this is the layer, the augmentation layer that I create. Later on, I'm going to add this layer to my network, right? And here is basically the documentation for rotation and random zoom and etc. from Keras API. Let me actually go ahead and show you. So these are different augmentation layers as of now available in Keras API. You can always create your own version manually, but I think, hell, it's not. Well, the one that's in Keras is good enough. And on top of that, usually we do transfer learning. We rarely get to train the models from scratch these days anymore. At least this is what I do. Okay, now let's go ahead and visualize a couple of these images with this augmented version with the rotations and everything. And this is a good practice just to make sure that you're understanding what is inside that tf.data set. We can, for example, use this .take. Basically, it says that give me only the first batch. From the first batch, we're going to save the first observation, right? So if I run this line, so if I do train underscore dataset .take 1, it's going to go over the first batch. Remember, the first batch had a size of 32. And then I'm going to say, let's go ahead and create an object called my image. And that my image is what? Is images, which is here, the first observation, right? Okay, so I can look at the shape. The shape is 180 by 180 by 3. So this is a tensor. We can go ahead and use PLT from matplotlib.image_show, but if I simply pass this tensor, it's going to complain. If I simply say do something like this, let me actually copy this and paste this, and let me show you the steps. So if I run this, it's going to complain. Well, obviously it doesn't understand the tensor. I can go ahead and change it from tensor to numpy array, so by doing something like this, but it doesn't work, because remember, we re-scale things between 0 and 1, so that's why we have to add this last step, which is as type, as type. So let's do it in the next cell. As type is with this u integer 8, right? U into 8. So this is our image. So again, when you're running this line, you might get a different number, simply because every single time that I do this, well, actually this is saved here. Every single time that I do this, right? When I take the first batch, it's going to be random shuffling inside that batch, right? So I get a different image, right? So when I do this, I get a different image. Okay, let's go ahead. We like this one. If you want to see how the rotation and this data augmentation is going to look like. So I'm going to run this cell. Basically, I'm not doing anything special here. I'm looking at the augmented images, going through a for loop of 16 images, right? And then I say, use this data augmentation layer that I just created, right? Here, data augmentation. basically I'm transforming the data, right? I have a transformer, let's call it a transformer, and I apply that transformer to the image that I have. So this is what I'm doing, applying this transformer to the image, save it somewhere, and then repeat this process 16 times and simply show it, right? So show that image that you just created and saved, and then again .numpy .astype change, make sure that we rescale it back. Well, we use these numbers for the scale, and we see it. Okay, so this is the original image. We have the horizontal flip, we have rotation, as you can see. Probably we should see some zooming here, right? This is a zooming thing. All right, now so this is, hopefully it gives you a better understanding what this transformation data augmentation layer that we just created is going to do to the data. And now we can add this layer to the network. So let's go ahead and do that. So I'm going to go ahead and create my new function. This is a new CNN builder. We call it CNN builder augmented. The input is exactly the same. I'm going to use the exact same architecture as before, but remember, right before the rescaling, we have to go ahead and add this data augmentation layer. And actually, this should be X. There's a typo here. Okay, and so I'm going to make sure that I make this change and push it to the repository again. So the first we're going to do data augmentation past the input, and the second one we are going to do rescaling past this X, and then on top of that we are going to simply just build layers, right? Conv, max pooling, conv pooling, conv pooling, flattening. Here I'm going to do dropout as well, because make sure when we're doing augmentation, we know that the model is going to overfit later in the course. In the training process. So I'm going to do dropout to just remove those overfittings extra. So this is extra regularization that we're doing. I can go ahead and add a dense layer at the end. And because we're adding a dense layer, I'm going to go ahead and add another dropout, right? So hopefully we will get a better performance. Let's see what we get, right? Again, the rest is pretty much the same. So the activation function sigmoid, inputs, outputs, and then I'm going to call this a new model. Binary cross entropy loss function, and we're keeping track of accuracy. All right, so let's go ahead and construct this model and look at the we can look at the, don't worry about these warnings. These are just some shaped warning when it comes to data augmentation, and but usually it's able to handle it. Do you remember in the last Python video I showed you that if you have a grayscale image, sometimes it complains. You have to reshape the input layer to the augmentation by using TensorFlow tf_expand, the expand dimension, right? Expand dims, and tf.expand dims, and then you have to squeeze the shape back to the lower dimension. For 3-color, for RGB color or 3-channel images, it seems that it's able to handle those things. This is our model summary. Again, you should be able to back out all these numbers, as before. So we used to have, let's see the previous model, how many parameters did we have? We ended up having 991,000 previously. Now we have a lot more parameters because we added this dense layer at the very end. So where is it? Yeah, we added this dense layer with 128 neurons. So whatever it is, it's going to multiply that thing to the flattening part. So that's where it's coming from. That's where the large number is coming from, right? Now we have 2.6 million parameters, okay? So I'm gonna go ahead and create another checkpoint because we wanna keep track of things and compare these models at the end. I'm gonna call it CNN augmented. And yeah, so by monitoring the validation loss. So this is our callback. Let's go ahead and run this. This is gonna take time. So I'm gonna run it for 30 epochs, but again, with regularization, most probably we need to run it for more epochs, but just for the sake of argument and comparison, I'm gonna run it only 30 times. You can let it run for 100 epochs, I don't know, 200 epochs. Okay, and this is a lot slower compared to the previous one because first of all, we have more parameters, but that's not necessarily the case. The data augmentation is something that's making it a lot slower. So just like the previous one, so the first iteration, the performance is pretty much the same as our previous model, maybe 51% in the validation accuracy. And yeah, I'm gonna pause the recording and let this thing run and then report the results. Okay, the model has been trained, we can go ahead and look at the output. So these are, let's see, let's look at the path for accuracy versus loss. This is a loss in the train and test. So as you can see, it's a little choppier than the previous one, and it seems that no, we started overfitting. So definitely I would let it run for more epochs. But now we can go ahead and run see how the model performed in the test set. This model that we call CNN augmented. It seems that we are getting an error. Let's see what is inside that. Again, this data augmentation layer, the sequential layer that we put together. Sometimes it will give you shape incompatibility, and this is exactly what's happening. And we can go ahead and manually change those things, or change the transformation layer in the data augmentation. Let's actually see what is the error. Input 0 of layer sequential is incompatible with the layer is the expected shape non 183. So this is not right. But the shape that we passed was non 18183. So this is a right shape. So we don't need to change the shape of the test set. But one of those transformers, those augmentations, was expecting something like this. So for the sake of time, what other solution? You can go ahead and then switch on and off, or look at the documentation for the sequential layers that you put together for data augmentation. But and frankly speaking, it didn't give me that error previously when I ran this one, but I don't know what's going on, so I need to dig deeper. But just for the sake of time, and this is let's say the data augmentation process, right? And I ran this before, and I think we get up to, actually in the train set it was working. This is surprising. This was working, the training part was working. And what did we end up with? So maybe the best model was doing a 70-80% in the validation set. So I don't know, maybe run it in a test set, probably we're gonna get 72, 73 kind of percent versus 70% without data augmentation. So this is basically doing CNN, comparing the benchmark with the data augmentation. The reason that I don't emphasize or overemphasize this data augmentation thing is that because nowadays we can do transfer learning, right? So I personally, I don't want to say never, but maybe the data set that you work with, if the classification is something like this, is this cat versus dog, we know that ImageNet dataset with 1,000 classes, which was the model were trained on 1 million observations. I can borrow those weights, right? And it is obviously the model that's going to outperform easily any kind of data augmentation or image augmentation. So that's why I'm not overemphasizing on this whole idea of data augmentation. If you're doing a very specific task, right? If you are doing an image classification and the images are very, very unique to your field, whatever they are, right? And that image classes are not one of the 1,000 categories in a dataset like ImageNet. Basically, the models have not been trained on those images. Then maybe, data augmentation is going to help you when you are doing, when you're using a small sample size. But in general, again, even if the classes that you're considering is not within the 1,000 categories of the ImageNet, we can still use the first layers of the larger models that have been trained. And this is exactly what we're going to do. So here, in our case, the dataset is, the classification task is cat versus dog. And we know that cat versus dog was part of the ImageNet in terms of one of those 1,000 classes. So I'm going to use one of the bigger models, let's say VGG16, and which have been previously trained on the ImageNet, and do transfer learning, right? So from the theory lecture, so this is a slide from the theory lecture. We talked about these, different classical architectures and maybe newer one, and the one that we're going to use here is VGG16. So we're gonna use this one, and basically what we're gonna do is transfer learning, and I'm going to show you both ways: transfer learning using feature extraction, and transfer learning simply doing fine-tuning. Using feature extraction is going to be super fast, right? Because as we talked about in the lecture theory, we are not going to unfreeze any of the layers, right? So all the layers are going to be there. So they are all freeze. So there is no trainable parameters there. We are going to borrow all these weights from the pre-trained model. And Then we're going to add our own dense layers at the very end. Basically rerun the entire model. So the parameters, the learnable parameters are here. These are the freezed one. And it's going to be fast because the extracted features, we're going to work with extracted features from the first part and add those extracted features to our model and make some predictions on those extracted features and come up with different classes. So this is a feature extraction method. Let me actually walk you through the code and I get to the fine-tuning part. Okay, so let's see. So this is a feature extraction. I'm going to go ahead and say, make it convolutional base, right? So we can call it anything. I'm following the code from Francois Cholet, the GitHub that I just showed you at the beginning of this. Okay, I'm gonna say from keras.applications.vgg16.vgg16, let's go ahead and import these weights. So the weights that the model have been trained on the 1 million observations of the ImageNet dataset with 1,000 different classes, right? I say include top false, so we most of the time we don't want to include this one, right? We know that because we want to add our own version. Simply, we're using these models to extract features, right? This is what we need: extracted features, and then apply it to our own model. And the input shape, it should be compatible with the input shape of your data set, right? We decided to go with 180, 183. That's it. So it's going to go ahead and download those weights. We can look at this model summary. As you can see, there are 14 million trainable parameters, right? So they are trainable, but the way that we're going to do for feature extraction, we're going to freeze them all. We're going to freeze them all, add our dense layers at the end, and only train the model on that. Okay, so this is the structure of the VGG16. You should be familiar with this structure. Basically we looked into that here. Okay. Conf pool, that's the pattern which is repeated in the VGG16, right? And then a couple of flattening layers and then 1,000 class classification. Okay, so these are the blocks. 1, 2, 3, 4, 5 blocks, and then followed by max pooling. Okay, so I'm gonna go ahead and extract these features, right? So let's go ahead and create our function. We're going to say get features and labels. So what is the goal? So the goal of this cell is to run this VGG16, borrow the weights from the VGG16 model, and then run it to our own data. So this is our own data. This is the borrowed model, and come up with the extracted features. So this is what we're going to do, right? So we're going to say this is a function, get features and labels. So if I apply this function to the train features and train labels, if I apply this function to our train dataset, which is a tf.data.dataset, we are going to come up with two things: the trained features, so these are the new feature map, and the trained labels. We're going to apply the same function to the validation set and test set, right? So let's see what is inside this function. So I'm going to go ahead and keep track of all the features. It's an empty list. We're going to append to that. All the labels, it's an empty list. We're going to append to that, right? We're going to say, remember, we're going to pass a data set, and that the object is TF. It's a TensorFlow.data data set. There are two things in it, right? Images or features and labels, right? We need to pre-process images if you want to pass it to one of these large models, right? And most of them come with this function called preprocess input. So for example, if you do VGG16, you can do .preprocess input. If you do exception, you can do .preprocess input, right? So we are going to pre-process the input first, and these are the images, the features, right, from the data set. And then we are going to create the features. Remember, if I use this conv-based model, so the model is there, it has been pre-trained, and if I use the predict, it's going to make some predictions on these pre-processed images now, and now I have features. Then we are going to go over all the images in the data set in a for loop, and then simply append them in our empty list of all features. So this is the way that we are keeping track of all the features. This is the way that we're keeping track of all the labels. And then, because I want to use it I want to add it to my own architecture, and TensorFlow is expecting a NumPy, so I'm going to do a concatenate the results. So I'm going to concatenate all features and concatenate all labels. So that's basically what's done. And we're going to apply this function to our three data sets: train, validation, test. All right, so this is going to take some time. I'm going to pause the recording and then come back when it's done. Okay, it seems that it's done, right? And look at that. First of all, pay attention to the last layer of your VGG16. It's 5 by 5 by 512. So we have 512 filters, and the spatial dimension is 5.5. So this is your feature map. And you can visualize it if you want, but of course it's not going to be, it doesn't make any sense visually, right? So let's scroll down and see what is inside this thing. So now we have, for example, let's look at the shape of a couple of them, right? Let me actually, let me go ahead and show you what do we have. We have train features. These are some 5 by 5 by 512 images from the train set, and these are the feature maps, and they're related labels. Feature maps, labels, feature maps, labels, right? So let's look at the shape of a couple of them. So for example, for the test set, if I look at the test underscore feature.shape, remember there are 2,000 images, 1,000 cat, 1,000 dog, and this is a feature map from the very last conv layer of the VGG16, which is a 5 by 5 by 5, 512. So we are here. We're here. Okay. Yeah, and we're going to use that one, pass it to our own model, right? So again, test labels, we're going to have 2,000 labels as well. So then, so the rest is pretty straightforward. We are going to put together a model. So just as before, this is our input. Look, but be careful, look at the input shape. The shape of the input is now 5 by 5 by 512 because this is coming from the feature map that VGG16 generated, right? And then we are flattening them. We are using a dense layer with 128. This is our own dense layer. We can play around with these numbers. We are adding a dropout to make sure it's not overfitting. And the output is a dense layer. Again, one node because it's cat and dog, sigmoid classification, sigmoid activation function. Then let's go ahead and build the model, and that's it. For the compiler, we're going to use binary cross entropy. Nothing changed here, right? So we simply, so that's what is the difference? So this is the whole point of it. Now the input is different, right? The input are the extracted features from VGG16. So this is our model. We can look at the model summary. And there you go. So this simple model itself has 1.6 million trainable parameters. Okay, and just if you want to see where the numbers are coming from. So for example, the last layer, remember, so this is where are we? So we flattening things. You know, if you do 5 by 5 by 512, you get 12,800. And now we are using the dense layer with 128 nodes. So 12,800 multiplied by 128 plus 128 bias terms. So this is where the number of parameters is coming from, 1.6 million. Okay, now let's go ahead and do the model fit. Remember, guys, you don't see that 14 million parameters here in the model, right? Because we're done with that, right? So once we made these predictions, so basically we were using those weights without touching them, without training any of these 14.7 million parameters, and then we made some predictions. Now the number of parameters in the model is just 1.6 million. That's it. That's why this approach of transfer learning is a lot faster. I'm going to go ahead and create a callback. So CNN feature extraction VGG16. So this is our first version of transfer learning, right? So we are doing this method. Let's see how it performs. Okay, so let's run this one, and then now, because we have a separate features and labels, we're going to go back to that tradition of passing those two data sets, right? So model that fit, it's expecting X train, Y train, validation data, again, X validation, Y validation, okay? Let's do 20 epochs. It's gonna do a decent job because again, we are using a very good performing model like VGG16, which is pre-trained. Okay. So right in the first epoch, the accuracy in the validation set is 97% right off the bat. So this is great, right? So, and you see it's pretty fast because again, we are working with the very low dimensional inputs, 512. So these are the filters, number of channels, and the spatial dimension is very low, 5. So that's why even with 1.6 million parameters, this is pretty darn fast. Okay, so again, this is great, right? Remember, the performance was 70%, right? When we constructed our own CNN. Now we are leveraging other models out there, larger models, and we get to accuracy of 97-ish%, right? This is great. So we can visualize these things, again, the performance valid accuracy path. So this is the accuracy path. We are, however, look at for the loss. It seems that right from the first epoch, the model is overfitting. So we can play around with this, with different components of the model. We can play around with the dropout layer. We can play around with the fully connected layer that we're adding at the end and things like that. Okay. All right. So now the model has been created, this one, and saved. Let's see what is the performance in the test set. Let's run it. Okay, so in the test set, it seems that we are doing 97-ish%. So this is great, right? So again, you might get 96, 95, depending on what initializations were used for the weights, random seeds, and etc. Great, right? This is doing excellent. So the last thing I want to cover in this Python notebook is how we do fine-tuning, right? So let's do fine-tuning. For the fine-tuning, we are gonna, we are gonna keep all these layers, the conv layers, freezed, and we unfreeze the last one. We talked about in the theory lecture why we unfreeze this one, not unfreeze this one, right? Because remember, if you're doing image classification, right, the very first, hidden layers or conv layers, the filters are extracting what? They are looking at, edge detection, line detection, pattern, texture detection, something like this. So maybe here we're doing some texture detection in the block 2 and 3. And so basically, if you're doing a cat versus dog, or bicycle versus motorcycle, whatever you're doing, the first layers are pretty much the same. You're talking about lines, horizontal, vertical, wavy, etc. So what you want to change is this one, the last part. So this is where more deeper in the network, and the filters are capturing higher level features, right? Like, for example, if it is cat and dog, it's capturing eyes, ears, and etc. If it is cars versus trucks, it's capturing, the height, the headlights of the car, and etc. Right? So for that reason, we are going to unfreeze, let's say in this exercise, let's unfreeze the very last block, and then add our own dense layer, and then retrain the entire thing. Okay, so this is where the term fine-tuning is coming from, right? So we're fine-tuning a pre-trained model. So this is our VGG16, and we are going to unfreeze the last 4 layers, right? So remember, the conv base was our VGG16 thing that we imported from Keras. We're gonna say, let's make sure all of them are trainable, and then we're gonna make a for loop, look at all the layers from this model, and say that let's go ahead and make sure that the last 4 layers are not trainable. Okay, so basically we are freezing everything except the last 4 layers. Okay, so now actually I can show you. Let's look at the conv base summary one more time. Conv base.summary. Show you what I mean. So here, you see the number of trainable versus non-trainable is different, right? So we have 14.7 in total, and we freeze the first 4 blocks, and the very last 4 layers, conv layers, are unfreezed. So that's why we have still 7 million trainable parameters, but 7 million of them are non-trainable now. Okay, 7.6. Now let's go ahead and put this model together. The input, remember the input shape now is, so we are constructing our own model, right? So let me go back to this. We are going to use our own input because we're not using the extracted features like feature extraction. We are going to use our own input and then train the entire model. 7 million of these parameters are not trainable, 7.6 of them are trainable, and then we're going to add a couple of dense layers, and then that's it. So that's why the input here is 180 by 3. This is the original input of our data set. We are going to say that this is the first layer, keras.application.vgg16.preprocessing preprocess input. So we are going to make sure that we will prepare the data or preprocess the data, the inputs, in a way that the VGG16 can handle it, right? So that's why we're adding this layer. Then we're going to apply those kind of inputs, the preprocessed inputs, to our conv-based model. So this is a conv-based model. Again, half of it is trainable. Well, half of the parameter is trainable, half is not. We're going to flatten things right after that. So flatten the output of this the pre-trained model and add our own dense layers, right? So the first dense layer with 128 nodes, use the dropout, and the output is, the rest is pretty much the same, output, model, and the compile. So maybe one thing that we're changing here is in the compile. The optimizer is, we could go ahead and use RMSprop. We are still using RMSprop, but we are changing the learning rate. So we're using a very small learning rate to make sure that, you know, here's actually what we're doing. We're going to limit the magnitude of the changes we make to the last 3 convolutional layers that you're fine-tuning, right? Because if the learning rate is too big, and it's going to mess up the entire weighting of the last 3 layers. Okay, so that's probably the only difference. Where's this number coming from? Oh, we have to pick a small number. You can try different numbers and see which one is performing better. Okay, so this is the model that we put together, right? We have an input layer, you know, batches of size 32 in image color images 180, 183. Then we are doing basically, we are adding this pre-trained model, right, with 14 million parameters, 14.7 million parameters. We are flattening things. We are adding our own dense layer. We are adding the dropout and then final output layer, right? Now, the new model has 16.3 million parameters. 8.7 million of it is trainable, and 7.6 million of it is non-trainable. So as you can see, there's a quite few number of parameters that we are, you know, the big chunk of it is for the VGG16 model that we are fine-tuning. So as you can guess, this is going to take a lot longer compared to feature extraction. So I'm going to create a model called CNN fine-tuning. So this is a fine-tuning version. And this is our callback. Let's go ahead and fit the model, right? So we will be using the train set. So guys, pay attention. This is, we are going back to we're passing one data set, right? Because we are passing our original images. So, which is a object type of tf.data.dataset. So again, the first iteration 93, not bad, right? And I'm gonna pause the recording and show you the output. Okay, so it seems that the model has been trained. Let's go ahead and look at the evaluation. Again, this is doing a decent job in the validation set. All right, so let's look at the metrics, visualize these paths, you know, for accuracy and the loss. And as you can see, maybe right after 2-3 epochs, the model's overfitting. But again, we're getting a decent accuracy, right? So maybe there's not much room to improve. And okay, so remember we saved this model as fine-tuning VGG16, right? So let's go ahead and see the performance in the test set. And so right now, so far we have 4 models, right? Our CNN benchmark, the augmented version, and the one we use transfer learning using feature extraction, and the transfer learning with fine-tuning. And we can compare the performance. So it seems that this is 96%. What was the performance of I think the performance, yeah, on the for the feature extraction, it was also 97%. So it seems that the one with the feature extraction, which was faster, the performance was okay. So let's go with that model, right? So what does it imply? It implies that whatever we added to the very end layers was not making a big difference, right? So this training this part, and there's a reason for that. The reason is that the classification is, the classes are dog versus cat, right? And this pre-trained model, VGG16, has already been trained on a dataset with so many dogs and cats. So we didn't need to basically train this very last layer. We could have simply used that one, the pre-trained model, on a larger dataset, 1 million dataset, and then simply add our own dense layers without touching the very last layers, conv layers, right? So this is exactly what's going on. That's why that simple feature extraction using VGG16 was outperforming our own fine-tuned version of VGG16, simply because the classes cats and dogs were already available in the ImageNet dataset. Okay, so we know that the feature extraction model was slightly outperforming the fine-tuning version. However, for visualization purposes, I'm gonna work with the fine-tuning model here because I want to visualize some of those misclassifications. And remember, the input of the fine-tuning model was the original images, But the input of the feature extracted model was basically the feature maps with the size of 5 by 5 by 512. So if you want to visualize those things, it doesn't make that much sense. So we want to work with the real inputs. So that's why, just for the sake of visualization, I'm gonna work with that model, right? So in real world application, of course, you're gonna pick the winner, so which was the model with feature extraction, because we don't simply just need to get the labels. You don't need to see things that I'm going to show you in the following part of the notebooks. Okay, so I'm going to actually change this to the fine-tune model. So fine-tuning. Let's see, there's no 6. Okay, fine-tuning. What do we call it? We call this one, right? So why is it not detecting that one? So let me actually, bear with me for a second. This is CNN, and then we do find. I'm surprised why it does not. Yeah, there you go. It cares. Okay, so this is the model that we want to go with at the end of the day. And now let's do some cool visualization. So we know that the class names in the test set are cat and dog. Let's visualize one of those images. So right, this is a dog, right? And there's an important thing I want you to pay attention, and it's whenever you run any of these TensorFlow data.dataset objects in a cell, in a Colab notebook cell, it's going to shuffle the data. So it means that if I rerun this, it's going to shuffle the data. If I rerun this, it's going to shuffle the data. So in order to make sure that at the end of the day you're comparing apples to apples, right images with the right correct labels, we are going to go ahead and we're going to look at keep track of the actual labels, prediction labels, and all the images, and we have to run it all in one cell. So what does that mean? So what I'm doing here is something like this. Let's keep track of the actual labels in the test set. It can be cat, dog. Let's go ahead and make some predictions, right? And I'm gonna concatenate them together, in a for loop. And let's keep track of all the images. And the reason that I put it all in one cell is that because if I do it separately with different for loops, then the labels will not match with the images, right? So for that reason, we have to run it in one cell. So what did we do is something very simple. In the test data set, there are two things: the features, the images themselves, and your labels. I'm gonna put together the labels, call it y-test. I'm gonna put together the predictions, call it pred test, and I'm gonna put together all the images and call it all images, right? Now, the only thing that you should just maybe pay attention is that I'm doing model.predict. Remember, what is our model? This is the model that we just loaded, the fine-tuned version of the VGG16, and I'm simply passing the input. These are the real input images, right? And variables is equal to 0 because I just want to make sure that we don't see any output here. If we change it to 1 for every single prediction, you're going to see that. Well, you're going to see that the model has been run, right? And finally, I'm going to reshape it to become a NumPy array vector. All right, so now we can quickly check out, for example, what is the shape of these test images. Remember, these all images, these are some images that we put together for all the batches, right? Because I didn't specify, for example, the batch number, so it's going to go over all the batches. And I can go ahead and use NumPy concatenate to put them all together and make them in a format that we can visualize it, right? So here's the shape of that test image. We have 2000, 1000 cat, 1000 dog, and there are 180y, 180y3. So this is nothing new here. You already know that, right? I can go ahead and look at the histogram for the predictions, right? So the model is doing an awesome job. Maybe 1000 class. This is not exact 1000 because we have some misclassification. Remember, the performance of this model was 96%. So it's not exactly 1000. You see there are some misclassifications. These are some other probabilities, right? Probability 0 and 1, right? So it's not purely 0 and 1, which is again, it goes back to that 4% of misclassification. But we don't want to work with probabilities, we want to work with labels. So let's go ahead and come up with this threshold. If the threshold is greater than 50%, call it 1. If it is less than 50%, call it 0. So this is what we call it our predictions, right? So this is the predictions. Now I have predictions and actuals. Let's go ahead and look at the confusion metrics. So from scikit-learn metrics, let's go ahead and import classification report, confusion matrix. First, let's look at the classification report, actuals versus predictions. These are 0, 1s, right? Not probabilities. Now we see that the model is doing a decent job for classifying both cats and dogs, 97% F1 score. Okay, so we can look at the confusion matrix as well. So there are 26 and 41 misclassification. The rest is correct classification. Let's visualize these misclassifications, right? Let's visualize, I don't know, 10 of them, 9 of them, and see what this monster model was not able to classify in terms of cats versus dog, right? It should be easy task for human being, especially, we the humans can easily classify real world images. We had hard time dealing with CFAR dataset, if you remember, or the fashion MNIST dataset, because they were very low resolution. But for real world images, humans, I don't know, the accuracy should be 99%, right? So let's see, what are these misclassifications? So we have done this before in the previous notebooks. Basically, we are visualizing, first of all, we are coming up with the index of the misclassified images, right? So he basically say that these are whenever the label is not equal to the prediction, right? We call it misclass, and we're gonna come up do a list comprehension and extract the index of those misclassification, right? Let's look at the first 9 of them. And so it seems that in the test set, observation number 69 was misclassified, observation number 100 was misclassified, and etc. Okay, so now let's visualize them. So I'm going to use this index and use all images from the test set and then put it in a for loop. So this is, if I run it, this is how it's going to look like. Okay, so again, we are going to go through all these misclassified images, and these are the indices, and I'm going to just plot from the test images. I'm going to plot that specific index. Make sure that you reshape it, because we have been rescale these things. Rescale it, not reshape it. Okay, so these are the ones that the model had hard time. Oh my god, what is this? It's Einstein. So I don't know why this was part of the data. This is so funny, right? So this should not be part of the cat versus dog. This is so weird. Anyways, this is the first time that I'm saying it, so I'm with you. So I don't know, this is so strange. But anyway, so this is, in reality, it is dog, so probably the model predicted cat. So again, I give it to model. This is not that easy. These are easier for human beings, right? So we, the humans, have no hard time saying that this is a dog. But this one is tricky, right? This one is honestly tricky. Is it a dog? Is it a cat? This one is easy for us, but for the machine was difficult. This is not fair. No, I don't know. We have to report this data set, right? This is a wrong picture. Actually, we have the index, right? So the index is number 7. So this is the picture. 1, 2, 3, 4. Yeah, this is the index in the test set, which is so weird. Anyways, yeah, and I hope you enjoyed this Python notebook. And I think the lesson learned from this one is that maybe it's the time that you train your model from scratch is we're past that time. So you have to specify the research question that you have in mind, you have in hand. If the image classification, if the images are regular images and you're within those 1,000 classes from ImageNet, regardless if they're from those classes or not, you should leverage those pre-trained models, especially if you have a small data set. And as you can see, we went from an accuracy in the test set of 70% to 97%, which was awesome. All right, I hope you enjoyed it. Until the next one, take care.